measuring, or at least calculating, the diffusion coefficient of a material based on impedance spectroscopy. And now we'll look at another technique to better understand properties of a material. So this intermittent titration technique is exactly what you think it is. You know, it's galvanostatic, so you apply some constant current, as you see here, with the pulse over time, okay, some time t. And how you develop this technique, or, you know, what is the pulse that you apply, how long you wait for relaxation, you can, that really depends on the material. And even for the same material, what we'll see in the part 2 of the electrochemistry series is that it can vary quite widely, and it depends on the material. You know, there has to be some understanding of the phase as well. So in terms of, you know, designing new materials, one needs to understand how current and older materials, you know, more conventional materials behave. And even then, I should emphasize, this is a model, right? So interpreting the data that comes out of GITT requires fitting, requires modeling, requires understanding the crystal structure. So Modest asked last time about lithium manganese oxide and the two-phase region and how that complicates things. And we started talking about lithium iron phosphate and how it also, you know, this material also undergoes a two-phase, has a two-phase region. And so, you know, how do you extract out the diffusion coefficient if you're now looking at diffusion in two phases, right? Ideally, you want one phase. And that's really difficult. I mean, for certain materials, that's just intrinsically difficult, because lithiation of heterocyte FePO4, right, into, well, also orthorhombic Li FePO4, you know, the olivine structure, it's almost immediate. So if you look at the stoichiometry, if you're at Li1 FePO4, and or so close to, you know, basically full lithiation all the way to almost zero, like basically FePO4, in those two limiting cases, you're in the one phase region. But as soon as you start to lithiate anywhere in the middle, you're going to be in the two phase region. Okay. So designing these experiments are not trivial, and interpreting them is not trivial either. And by that, I don't mean it's difficult. You apply a pulse, the computer will do it for you. But I mean really interpreting the data and the physical processes that are happening. It is complex. That's what I mean by trivial. There are many things to consider, understanding what crystal structure the material is in, you know, doing the refinement, doing, and also the local structures and knowing what rate you're at. So all of these things go into, you know, really planning an experiment well, so that one can then interpret the data as best as one could. Okay. So, but fundamentally, for all materials, for GITT, what you're trying to do is you apply this short pulse, right? There's going to be some increase in the voltage. So I'll try to do it here and not wave my hand at the screen so much so you can actually see the recording. Right, so there's going to be some increase in the voltage that you see here. And then at the end of the pulse, so this time t corresponds with the end of this pulse too, you'll see that there's going to be some relaxation, and then it's going to reach equilibrium voltage in this particular instance, okay? Batteries are always out of equilibrium. So what I mean by that is, for a certain composition, you know, let's say you lithiate a little, you do this, you know, you apply the current, you drive lithiation a little bit, you know, under discharge, and then you let it relax. How long you let this relaxation time goes for, that's up to the person to decide, and, you know, to the experimenter to decide. And honestly, depending on the thickness of your electrode, sometimes it is not at all feasible to ever reach true equilibrium, because that could take like years, you know, once you, so we'll go into that in depth with lithium iron phosphate. So you have to stop it at some point, right? So this technique takes a long time. I mean, it takes months just to study, you know, do a proper GITT experiment. But what you can get out is, you know, some useful information about the diffusion coefficient with care. right? And then to do that, you take the ratio of this delta ES going voltage difference from when you first applied the voltage, when you first applied the current, divided by this change in the jump in the voltage. And then everything else is just normalized by, the molar volume of your material divided by the area and how many moles that you're transporting divided by, the pulse time. So everything else is already, in the experiment and set up. So basically you measure the ratio of the voltages and you can extrapolate out the diffusion coefficient. Okay, so that seems simple enough, right? You excite, you apply a pulse, you relax, and you let it wait. And the equilibrium voltage should really track the discharge in your charge curve. Very similarly, like when you do, let's say, galvanostatic cycling under constant current, okay? Okay, so that's all nice and dandy. This particular example is of lithium iron phosphate. And so the next part 2 goes into depth, this study that illustrates why one has to do GITT with care, especially for materials that undergo 2-phase region almost immediately. So what I mean by that is, right, when you have an OCV, let's say, it's 3.5, 3.6 here for lithium iron phosphate, you see your capacity, you could see, well, if there was X plotted here, you could see that upon charge or upon discharge, that you go into this plateau 2-phase region almost immediately. So in terms of 1 phase, you're basically operating as close to 0 or as close to 1 in terms of lithium. So any numbers that you see, any values of diffusion that you see reported in the literature, that's just the apparent diffusion coefficient for the 2-phase region. And so when you do GITT, what you see is, you apply a pulse, relax, if you track the voltage as a function of time, right? You see here it mimics the plateau over these many steps for both the charge and the discharge as well, right? So that's what we're looking for. Before I jump into the GITT details, I also just wanted to highlight, a common technique to round out part 1, where I just go through all the techniques, is galvanostatic cyclic. When you apply a constant current to discharge, so reduce or charge or oxidize the material, this is useful because it allows you to measure then the voltage output, as a function of capacity, gravimetric capacity that you can normalize by the active material that you put into the electrode, so that's fine. By time, by composition. So how much X is in the compound. So that's particularly useful. So galvanostatic. In terms of why you would want constant voltage instead of constant current, is there are times when, let's say, when you're working and trying to integrate with real devices and you're working with electrical engineers for modeling and understanding, the state of charge and the state of health of like entire battery system, say a battery management system. Now we're talking about not just a cell. That's what I've been talking about thus far, right? Just a material within one cell. When you go to the battery pack system, when you have multiple cells in a stack and then multiple stacks in a whole module, and then you put the whole module into, let's say, an electric vehicle or whatever their end use is, it's easier sometimes to be able to predict based on constant voltage, how much charge a system has left. So you design, your measurement for what you need out. If you want to know, okay, what is the voltage as a function of charge, you're going to use galvanostatic cycling and you're going to apply constant current to do so, to charge and discharge. Okay, and so in terms of the typical voltage curves that, well, given that you all work in the battery area, I'm going to assume you've seen something like this. Okay, and if you haven't, let me know. I'll review in greater detail. But typically you see these curves where If the material is not lithiated, then you see the discharge where then you lithiate the material. Or if it is lithiated, then you'll see the charge first to delithiate the material and then relithiate again. Okay, so this is particularly useful because it immediately tells you, okay, upon discharge, how much capacity do I get? Here, I've drawn this particular schematic where there is a little bit more charge than there was discharge. So already you're seeing this particular material is undergoing, there's an overcharging. So there's got to be some secondary reactions, there's some side reactions, maybe SCI is forming, and also I have decomposition of some sort, and there's extra charge that's not related to the original material, right? So if you normalize by grams of your starting material, then if you have decomposition and you have spurious side reactions that are contributing to charge, you could potentially see something like this. And this is quite evident when you work in, let's say, lithium sulfur battery, you see overcharging quite a bit because there's polysulfide showing, there's decomposition of the active material, there's all of that. That is not, when I say real, I don't mean you don't see it, I mean, it's not related to the active material that you were initially interested in. It's indicative that there's some other secondary processes that are going on. Okay, so this particular representation is useful for that reason. You immediately see something useful that's telling you about the reaction that is happening. The other representations that you'll see, not only do you see capacity on the x-axis, right? So here, see capacity, but also the number of moles of lithium. So that's also useful to know the extent of the reaction, how many lithium ions have been transported per formula unit. So that's useful. The other representations that you'll see is, something that looks like this, where you have potential as a function of capacity, but then instead of representing the charge like this, it's actually just flipped, 100, the mirror 180 degrees. That's useful because then you could see the voltage difference a little bit more readily. That shows you how much energy is lost in terms of reversing the reaction. So if you see here lithiation, actually here it says magnesium. So you introduce magnesium ions into this particular compound, titanium sulfide, and then you remove the magnesium ions, you could see that there's a lot of energy loss, right? It's not as reversible as you think. So you want to see, the voltage differences be as small as possible, right? That tells you that the system is highly reversible. Okay, so this representation is also useful for that reason. So this is why you see a number of representations of the galvanostatic cycling plots the way you do, and sometimes it's also historic, but you plot for what you want to show first and communicate. This is also particularly useful in both representations. You'll see that you can track the capacity fade pretty readily because you can just look at the axis crossing and you see, okay, this is per cycle at the same C rate. This is at different C rates at either at elevated temperature or close to the room temperature. So you could see, C over 50, but at room temperature, you don't get as much capacity out as, faster rates, but at elevated temperatures, right? So it's pretty useful either way to have either representations in this case. Now, the other way one could also represent the data is to show the first derivative of the galvanostatic cycling. So if you see for this particular example here, lithiation of this one compound, so you see the potential as a function of capacity. So that's a common plot. But what's also useful is instead of just looking at by eye and saying where's my first plateau, the most reliable way is just to take the derivative of the data, and you can overlay that. So you can then overlay in GCPL the black curve here right? That's the first derivative, dq dv, as a function of potential. But when you plot it like this, it's less evident where the reduction and oxidation peaks are as it pertains to your galvanostatic cycling plot. So if you rotate it 90 degrees, then you could see that your first derivative peak really should line up. The voltages should line up with exactly where you see the changes happening over here in the original plot. What's also interesting is you can overlay cyclic voltammetry data. So we haven't talked about cyclic voltammetry here, but essentially all it is you apply some a voltage sweep. So you can, so that means the current response is going to be different. So you can apply a really fast, millivolts per second all the way down to microvolts per second. And what you want to see when you're sweeping these different rates is there a dependence of your material on frequency? And typically in real materials, the answer is yes. Now, people have also tried to calculate the diffusion coefficient based on where these peak centers are. So the center of these peaks, you can fit a peak here, look for the center, and you could do that, except typically CV is done beyond what's called the kinetic limit of the electrochemical cell. So that means you're sweeping too fast. Even when you slow it down, you see the resolution of CV versus the first derivative of your galvanostatic cycling plot. It's quite broad, right? So it's particularly useful if you're trying to look at, where's my reduction potential? Where's my oxidation potential? CV is typically the first thing people do. And that does give you some sense. It gives you a range, but if you don't slow it down enough, your sweep might be too fast. Your material's not keeping up with your sweep rate, and thus it's not really representative of what's happening in the material. Right. So this 2017 paper from Linda Nazar's group really goes into great detail as to why you would want to represent the data like this and why you would want to do galvanostatic cycling to understand the redox potentials of the material. Okay, so that's particularly useful. Yes.
On the previous slide,
Mm-hmm.
I always wonder when they present data in terms of potential versus capacity.
Yeah.
They also put another axis.
Yes. Like on the right.
Moles of lithium corresponding to that capacity.
Yes.
When I look at it, sometimes during the first cycle, like we just talked about, you may have extra capacity, not related to your material per se, but it may be related to the composition of SCRs.
Yeah.
But all you measure is the amount of current that is taken to do that. So you just quantify that, saying, this is the number of lithium consumed.
Yeah.
Plotting it there. But it's not really telling you anything about your material itself if you have that extra capacity that's not related to it. So you might interpret that as, maybe my material is being decomposed by this extra lithium.
Right.
But it might have nothing to do with that. And so sometimes I'm what's the best way? Is it, can we just forget the first cycle sometimes and just calculate that lithium after the first cycle to represent those?
I guess, is it best to forget about the first cycle and then just represent and just plot and say this is cycles 2 and on, or even 3 and on, right? Because some commercial cells are pre-cycled for a few cycles anyway, right? And I suppose, yes, if you communicate that entire caveat. That's what I concluded in reading all the literature thus far is just that it's all in the fine print. Comparing apples to apples, you can really only do that when you start to try to normalize. And thus far, there is no standard per se, unlike the photovoltaic industry right now, right? Where before you can claim that you have any increase, like official increases in quantum efficiency, right? Your cell has to be tested by an independent lab like NREL or right? You have to send your cell to a particular lab so that it's measured under standard conditions. And I think we're moving to that, but until we have some standardization like that, where, you know, for a certain material, it has to start from a certain composition, right? So there's no hysteresis, there's no memory, there's no lithiation loss, right? Then once you understand your starting material and you can fabricate a cell and then you send it to a testing center under identical conditions, then I think we can then start to normalize across the electrochemistry across cells. Now, I think the way people are doing it now, which is just to report what they've done, is fine in the sense that as long as you're transparent and you say, you know, this is the characterization of the material, this is what I think the material is starting with in terms of porosity, in terms of, you know, whatever material property that you can possibly, you know, report, and then plot it, but explain how you've done it based on what everything you just said. I think that's the best we can do. You know, it's just that. But in terms of, you know, your secondary question of the meaningfulness and the utility of the X mole, you know, there, I think it's more of communicating, yes, as you said, you know, the moles of lithium that have been transported, but whether or not they're all stuck in the same, you know, they're moving in and out of your active material is a whole nother question that further characterization needs to follow and be reported. Yeah. Yeah. No, it's I mean, you touched upon, you know, the point of standardization and how we report. I mean, the fact that there's been different ways of representation too, it shows you how there isn't one way of, there isn't one standard. Yeah. Okay. I put in here C rate too, to go back to the discussion that you had earlier about, you know, why is this useful? Now, when we also report rates, I think it's particularly when it comes to galvanostatic cycling, we're given at times you know, numbers that correspond to C rates. The more useful number would be the current density that's applied, you know, either by the area of the electrode or by the active, normalized by the active mass in the material, you know, because that's much more useful. I mean, you could also just look at the galvanostatic cycling plot and say, okay, what is the capacity that's been achieved, and sort of estimate, you know, if you know the number of moles of the intercoolant that has been transported, then you could say, okay, if I know my theoretical capacity is 1,000 milliamp hour per gram for X moles of lithium, and what I see, you know, achieved it, you know, or you know, that's been cycled in 1 hour, then you can backtrack that, and you know what the current density should be. But if we all report current density, then there's no extra calculations that have to be done. You can just say the current density is, you know, I applied, I mean, this is obviously a very large number, but I use, you know, nice round numbers, you know, for one particular cell, you're probably dealing with more like microamps, you know, per gram. But, you know, in this particular example, you know, then it's easy to say, okay, I can repeat your experiment if I apply 1,000 milliamp per gram, you know, that's what, or per centimeter squared if you're working with, let's say, you know, whatever electrode form factor you're working with. So, but it is convenient because then it tells you roughly how long something's been cycled, you know, C over 10, C over 2, that, you know, it tells you, you know, the magnitude of the cycling. But once again, you know, it's not so standardized. And if you're trying to study a material within the confines of a particular region, like you don't want to cycle, you know, not that lithium cobalt oxide is the latest and greatest. We moved on from lithium cobalt oxide a long time ago. But let's say, you know, you're working with lithium cobalt oxide and you're never, you know, you never cycle to 272 milliamp hour per gram, right? You really want to study that 0 to x equals 0 to x equals 0.5 region. You cut everything in half. You can rescale your entire discussion and just say now 0.5 is my theoretical capacity. I never want to go past that. So my 1C is how much of that, 135 million pound per gram I'm going to achieve in 1 hour. So you can rescale your entire discussion too, because now your theoretical capacity is half of that because that's what you're targeting. So communicating all that is key. Okay. Okay. All right. Now we're going to go into part 2. All right. So now let's really dig deep and talk about diffusion coefficient of lithium iron phosphate from GITT compared to EIS, and also different types of form factors, different types of ways of growing lithium iron phosphate. So we'll talk about, like, say, single crystal versus powder, porous powders that you try to compact into a composite. So we'll talk about all of that, but we're going to review this plot here and look at, okay, so if you have lithium iron phosphate, what you expect is a 2-phase transformation. Now you can bypass that. So this is not the voltage curve for fast charging. This is for standard, like C/10, C/4 even. But if you try to charge really fast, my comment about lithium iron phosphate having a 2-phase region becomes moot, because then what you could do is bypass nucleation by charging really fast and establish a single phase metastable solid solution. So you're always in a 1-phase regime. You can do that at like 5C, 10C. So you can do that. So materials will, respond accordingly. So that's what this science paper is about, is establishing the fact that there could be this, so the 2-phase region, so LiPF, FePO4 is denoted in this blue color. The heterocyte phase, FePO4, is denoted in this like pinkish color. And so in a traditional, just lithiation and delithiation process, you have nucleation of the secondary phase, and then eventually it transforms. So it goes from this blue, there's some nucleation, and then there's a phase boundary front that evolves, and then you achieve your secondary phase that you see here in this hot pink, and then everything becomes hot pink. Okay, so it becomes the other phase. What you can do is bypass it and achieve fast charging, and you get this metastable purple phase, which is a 1-phase solid solution. And then when you, let's say you charge really fast, you stop the charging, and then you turn off the current, and then there's relaxation. What you'll notice is the single phase region will actually relax and then go through the 2-phase region again. So that does happen. Now, so you can achieve a 1-phase by charging really fast, but when you're not doing that, typically this material goes through 2 phases. And so what you can do is try to study, how, if I'm in a 2-phase region, what happens when I actually try to measure the diffusion coefficient, and what sort of signal will I see, and how do I know that I shouldn't be doing this? Okay, as in you can misinterpret or overinterpret the data. So that's what we're going to talk about. Okay, and here's some of the details for this particular experiment of GITT applying a 0.31 microamp pulse for the electrode per centimeter squared of the electrode material, applying that for 30 minutes and then relaxing for 10 hours and waiting and see. Okay, so that's the GITT experiment. EIS is pretty standard, 100 kilohertz to 10 millihertz, very standard. And then, but in particular, they measure after relaxation for 10 hours. So when you set up a coin cell or whatever cell, right, you never just start measuring. you want the cell to relax and proliferate for X number of hours, whether it be 4 hours, 10 hours, overnight, even. That's pretty standard and typical. You want to wait for a long time for your electrolytes to this liquid electrolyte, right, for everything to sort of proliferate and then measure. Okay, so that's this experiment. So they did do cyclic voltammetry. So you could see, okay, if you take the CV, you rotate it by 90 degrees, you could see that indeed there is a difference and a dependence in the sweep rate. So if you rotate your head a little bit, you'll see that they swept from 0.01 millivolts per second all the way up to a millivolt per second, which is really, really fast. So there is a dependence in the rate. That means your material is right there. It's diffusion limited. It does respond to how fast you sweep through the voltage in your material. Okay, so you can extract what the diffusion coefficient is from cyclic voltammetry. So you can do that by using the Randall-Sachik equation, where you plug in everything. So all of this is known, and so you can backtrack out the chemical diffusion coefficient, and you can track the IP, so the peak center for both the cathodic and the anodic peaks, right? So upon reduction and upon oxidation. So here, if it's lithium iron phosphate, it's already lithiated, then you're going to remove the lithium and then re-lithiate. Okay, so oxidation and then reduction. Okay, so if you do that, then you can get the IP as a function of the sweep rate, the square root of the sweep rate. And you can get both the diffusion coefficient for lithiation and delithiation, because those two processes are going to be have different rates. Okay. So you could see that in this range, your process is going from about a minute and a half all the way to 17 minutes, depending on how quickly you're sweeping your voltage. Okay, so right now, so far, the order of magnitude, it's 10 to the negative 14, according to CV, right? Slightly different, 2.1 versus 1.8, but not extremely different, which is foreshadowing what's to come. Okay, so there's that. Then you could do GITT, which they did, right? And what you want to see is, well, you first have to assume that your material follows Fick's second law, first of all, okay? And that's not always true if you have secondary processes that you don't understand. So for a material, let's say, let's not consider the SEI, let's not consider like all other processes, let's just think about diffusion. Then you could do that. So here they apply, excuse me. So here they apply their pulse, right? And then relaxation. Okay. So what you can do is you can measure the OCV as a function of composition. So here they have y minus x, which is why this is backwards. Typically you expect something that looks like this, right? But if you look at the way they denoted, it's not one LIX, it's 1 minus x. So the whole plot is flipped 180 degrees. So if it looks a little odd, like this is not the charge discharge curve you would expect, that's because the way they represented data is for some reason 180 degrees flipped from what you would expect. Okay, great. All right, so what you can do then to get DEDX, you measure the OCV, you lithiate, measure the OCV, and you can plot all of that for lithiation and delithiation, or discharge charge, and you get the DEDX plot. So you get those values that way. Okay. You could also get the DEDT in the same way. Okay. So here you can plot the voltage as a function of DEDT. So DE is the change in voltage as a function of the square root of time, as a function of X, the composition. And you'll notice that this is only done for this fitting in this particular regime. So dE over dt, square root of dt, is only done in this linear regime, not in the plateauing region. Okay, so already there's assumptions about, you know, what happens when you wait for longer periods of time. That's totally ignored. Okay, so if you then look and say, okay, if I only work in this linear regime because I don't know how to fit the other data, then you say, okay, if the time is, you know, between 10 seconds and 100 seconds, what processes does that, you know, does this time scale correspond to? Is it Warburg diffusion? Is it diffusion of your material? It's a little fast for that because the Warburg impedance typically occurs when you do the EIS, right? You see that Warburg impedance really comes up when your frequency gets to about 10 millihertz to maybe 100 millihertz, right? So 10 seconds to 100 seconds, if you convert that to frequency, if something's happening once every 10 seconds or once every 100 seconds, it's, you know, you're looking at 10 millihertz to 1 millihertz. So it's not really within the Warburg impedance regime. So there's like something else that's there that's like built into this diffusion coefficient and voltage response that you're measuring. All right, so already something is telling you it's probably not just diffusion of lithium ion in your material by just looking at the time that it takes, okay, in the voltage response. Okay, but if you really wanted to, you can still, you have these values. So you plug it in to your equation, right? You plug it in, you have dE dx, you have dE over square root of time. And all of this is, you know, just numbers that you can plug in based on how you prepared your electrode. So you could do that and you can get this funky looking plot that you see here. So what you're seeing is there is a different diffusion coefficient near the end members. So when you have X is 0, so that's fully lithiated, versus when X is 0.9 or 0.8, so close to D, basically mostly, you know, delithiated LiFePO4. And then there's this like dip in the diffusion, right? So that's basically corresponding to your entire two-phase region, that your diffusion coefficient is dipping. That's because there's a phase boundary that's evolving as you're changing X. Okay, so that's lumped into the diffusion coefficient of just like lithium ion in one phase. All right, so there's a dip. It's telling you there's something else that's going on. Now, if you do EIS to compare with GITT, what you see is, okay, so so here they did you know, EIS of lithium iron phosphate at different compositions of lithium ions, and they see something similar where the Warburg coefficient also dips, and then the charge transfer also dips, but the diffusion through, you know, the liquid electrolyte that's in the system doesn't dip. Okay, so that's good. The red part is pretty good, right? It's not electrolyte dependent, which is very good. But there's a dip in the charge transfer. There's also a dip in the Warburg coefficient, which means there's going to be a dip in your diffusion coefficient. So both EIS and GITT are now starting to agree that they're saying there's something that's not purely just lithium ions diffusing through your system, because there seems to be a dip. Okay, and if you calculate it, you get this range based on composition. It's going to be somewhere between, you know, 10 to the negative 18 to 10 to the negative 14. Okay, that's a very wide range as well. Okay, so then let's take a look. So the first source 1, compares CV, GITT, and EIS. And there's a range between something 10 to the negative 14 all the way down to 10 to the negative 19. And so this is a thin film geometry, okay? Now that's going to be different than if you're trying to measure these, you know, the diffusion coefficient going through, let's say, a single crystal. And so this particular study by Yeah, so by Amin in 2008, on the single crystal, does a really good job of trying to actually track down the diffusion coefficient along different axes as well. And so that's how you can tell that the fast diffusion is along the B axis or along the 010 direction for this orthorhombic material. So while single crystals, right, we're not going to fabricate any commercial cells with single crystals, it's particularly useful to actually try to track down diffusion along all the independent axes that way. So this table just goes to show you the range of diffusion coefficients that you can get on just one material with one study with different techniques, and also the same technique across like different types of form factors for the same material. Okay, so something to keep in mind when you're trying to design new materials and say, well, if a material has a tunnel structure, I would expect the diffusion coefficient to be like this along this direction, for because there's a lot of caveats and asterisks that go into saying that. And in reality, all you can really say is the apparent diffusion is a certain value, and not necessarily always be able to say that it's solely because of a certain crystal structure. So it's all tied together. Yes.
So how do companies go about mitigating the variability of like the material as you kind of scale them up? Like, let's say you're going from a point cell all the way up into like a prismatic cell or something like that. Like, how do you mitigate that variability? Is there a guarantee that it will perform the same way, or is it just not like that?
No. Well, the short answer to your question is no, there is no guarantee that when you scale up from a coin cell performance, that the material will work well in a pouch cell, in a prismatic cell, and then eventually in a module. There is no guarantee. That is the short answer. The more nuanced answer would be, more studies, right? I mean, if something is promising in the coin cell regime, then you could start to speculate and say, okay, if I scale up, there's potential that this material would still perform well with more mass loading in, let's say, a pouch cell, or double-sided cell, that kind of. So I guess that is sort of like a soft answer for everything in life, right? Nothing's guaranteed, but there are. So I'm not trying to give you like a very weak answer. I'm just giving you statistical probability. So a lot of the studies that that show really promising, let's say, fast C rate or high capacity, when you then go from coin cell to increasing mass loading and area loading to the form factors that you mentioned, that's not always, it doesn't always translate. And you see that when you look at when studies come out of a material and then commercialization efforts, there's a huge lag in between, because of all of the things that you just said, because of like all the due diligence that people are trying and the engineering that goes into then fabricating something. Once, making that leap from materials design, understanding something fundamental about a material, and then translating it over to like a device or, that sort of thing. That's not to say that we haven't had a lot of successes and, it's in that, that's not saying that it's impossible. That's just saying that it really is the leap, in between. So what can you do, right? So you can think about the engineering aspects, like, okay, so the material performs well in a coin cell. What happens when you translate and you try to have more mass loading? Is SEI going to be more of an issue? And one of the ways is you just do it and have, and make the measurement, because sometimes things are not apparent until, not everything is predicted ab initio or a priori, but we do know enough now based on, all the transition metal oxides that we've encountered, even the sulfides that have been building up since the 70s and 80s, with Stanley Whittingham and titanium disulfide and the sulfur and all that. We have a bank of knowledge now that we're not starting from scratch, but So engineering isn't like, working in the dark. It is guided, but in terms of someone saying, oh, my 3 coin cells worked really well, and you publish a paper, that doesn't always translate.
Still kind of a valley of the dark.
Yeah. So that's like the very long asterisk to the commercialization of any material that you can design from the beginning. Okay. Okay.
I also have a quick question.
Yeah.
The form factor is really just talking about the morphology of the electrode, right?
No, sorry. It's the, well, okay. I sort of, okay, sorry about that. I sort of put all those things into under one umbrella term called the form factor. Yes, it is the electrode form factor, as in thin film, but it's also what the material is like before you put it into an electrode. So here for thin film, they like grow, like it's post-layer deposition. So they grow it onto the electrode. Like the electrode's there, they pulse in the precursors and it's grown onto the electrode. Now that's different from, let's say, the reference 5 where it's spherical particles or powder composite. There the material is synthesized like in hydrothermal flash, it's preformed and then made into a composite, and then, electrode, blocking electrodes or like a cell is then fabricated.
Okay.
So all of that was just sort of subsumed under form factor, and I kind of brushed over it.
That makes sense.
So no, it's not just the electrode. Okay. Oh, okay. And we will pick up here next time for titanium disulfide and talking about the diffusion coefficient and sulfide materials. And yes, and there was a question about distribution of relaxation, DRT. So I will briefly touch upon that in response to that request. I was actually going to move on to anion redox material, but I'll put that in next at the beginning before we move on to anion redox. Actually, before we continue here and then move on to anion redox. Okay. Thank you, everyone. I will see you next time. I've been promised this will get fixed Friday. Don't hold your breath.